Here's the first section to topic 8. We're going to begin by talking about fuels and different types of fuels. First things first, the definition of a fuel is a substance that can release energy by changing its chemical or nuclear structure. So the big thing you need to remember here is that fuel is a substance that releases energy in its chemical or nuclear structure. So some examples that we have here are coal, oil, and nuclear fuel. We'll talk about more, such as water, hydroelectric, wind, solar, etc. But these are the main ones that you should be aware of at this point in time. So to start this off, when coal burns, it changes its chemical structure, which thus increases the kinetic energy, which is directly related to temperature. Ke is directly related to temperature. That's something that you would need to remember there. Fuel alone cannot make a machine then do work. So unable to make a machine do work, an engine is then used. Okay, an engine is then used. This engine must be used as well as the fuel to get a machine to do work. Yeah, the kinetic energy is there, and by definition, the ability to do work is to have kinetic energy. But to turn this fuel into a usable form of energy, it needs a helper outer, and that helper outer is an engine. So what we really need to refer to here is the second law of thermodynamics, in which it is impossible to take heat from a hot object and use it all to do work without losing some to the surroundings. Now, obviously that means that some of the energy is dissipated, it's not lost, okay? It's just changing forms, like friction is present, for instance. So with that in mind, reasoning here, if you transfer thermal energy to a body, then the molecules start to move faster, which means that the molecules are now spread out. Obviously, we're looking at gases here in this sense. Once the molecules are spread out, you cannot bring them back together. This means that you cannot avoid the transfer of some energy to its surroundings. Transfer some of this energy to its surroundings. So that's kind of like going from mechanical, Ke to Pe, Pe to Ke, Ke to Pe. There's going to be some that will be transferred into non-mechanical energy, such as heat, light, and sound. More so in this scenario, we're going to be talking about heat. It is also why, the second law of thermodynamics, is also why we cannot create a 100% efficient machine. This is called a perpetual motion machine. The machine would be able to perpetuate itself. Moving on from there then. Energy degradation and power generation still continued by the idea of the second law of thermodynamics here. This is what we look at how we use energy. We also talk about the law of conservation of energy. Therefore, we cannot make energy. We can only change it from one form to another. Two ways that we can do this is by transferring energy in a non-mechanical sense, such as thermal, i.e. heat energy, and by doing so, we are thus doing work. So by transferring energy and by doing work, we are using energy degradation, which is pretty much the basis of the second law of thermodynamics, which leads us to this idea of entropy, chaos, disorder. It also has to deal with temperature, increases in temperature. Going back to that first slide, you have Ke, you also have it directly related to temperature. So the more spread out energy is, the more degraded it is. Therefore, thermal energy is the most degraded form of energy. That's good to know there. Thermal energy is the most degraded form of energy. Once energy becomes thermal energy, we can never get it all back. All energy eventually turns into heat. Therefore, the end of the universe would be at the point when everything is now at the same temperature. Because if everything's at the same temperature, then there's no change in temperature. And if there's no change in temperature, then there's no kinetic energy. If there's no kinetic energy, there's no movement of molecules. Stop, all right, is pretty much what would happen. So once again, I'm just saying, referring to the second law of thermodynamics here. Examples of energy transfer. So I want you guys to try some of these out. Let's see how many we know. Energy transfer must always lead to some thermal energy being transferred to the surroundings. So think about a light bulb. A light bulb is going to convert electrical energy into what two forms of energy? Electrical energy is going to be converted into, well, what happens when that light bulb turns on? You get light and heat. light and heat. Okay, what about an electric motor? An electric motor. This is going to convert electrical energy into, well, what do you get from a motor? Okay, what's going to happen? Like the batteries are put into the system and you're going to start running that car, like a remote controlled car, for instance. That electrical energy is going to be turned into mechanical and heat. Okay, so what about a battery? Go to the store, buy some batteries. Batteries are obviously chemical energy. Okay, we're clear on that. All the way back to like topic 5, we were clear on that one. This chemical energy is now going to be converted into, well, I'm sure you know one of them, which is going to be the heat. It's electrical and heat energy. Next that we have is a car engine, the engine in cars. It's going to convert chemical energy to mechanical and heat energy. And then lastly, solar cells are going to convert light energy into electrical and, well, what's one of the main things of why someone would put solar panels on their house? So they could heat their house. Okay, so here's some good examples of energy transfers for you guys to refer to, please. Okay, Sankey diagrams. You must understand how to read a Sankey diagram. I see them everywhere in your IB stuff. Like, if we would choose an option that would have Sankey diagrams that were necessary for them, I guarantee you'd have a question on them. You're going to have them on paper 1 questions. You most likely will have them on a paper 2 question. They're pretty easy to follow, but not unless you start looking at them and understanding why did they draw it that way. Okay, so Sankey diagrams. Used to visualize the flow of something, such as energy, as it changes from one form to another, or different ways of producing useful energy. So what you're looking at here is the width. Well, that didn't work out well. What you're looking at here is the width of the band, okay? As the width decreases, the amount of energy is decreasing. That's what it's trying to tell you. So obviously the thicker band, 1,000 joules, is going to be the basis of energy. Therefore, if you would look at a car engine's Sankey diagram, think back to this slide, the car engine is going to go from chemical to mechanical and heat. So chemical should be the thickest, the widest band. It is the most energy. The second most is heat, the third most is mechanical. Please make sure you click on this link here after we're done watching the video or at some point so you can review some Sankey diagrams. Very, very important to look at the amount of energy flow through a Sankey diagram. Okay, generating electricity, very useful form of energy. It can be sent from one place to another through wires, can be produced from many forms of energy. That's kind of what we're going to get into here. You need a generator in order to do this. The point of a generator to convert mechanical energy into electrical energy. Generators are going to convert mechanical to electrical. Here's just a nice picture showing you all this. We'll talk about turbines a lot throughout these notes. Efficiency of power stations. Well, it's going to depend on a couple of things. The first thing it's going to depend on is the design of the power station. Also, it's going to depend on which type of fossil fuel are you using, oil, coal, etc., to generate the electrical power. So here's a really nice Sankey diagram for you to look at on the efficiency of power stations. Please make sure you do take a second and look at this slide. Electrical generator. If a wire moves in a magnetic field, the electrons inside it experience a force, right? Causing them to move to one end of the wire. Think all the way back to topic 5 when we were talking about gravitational forces in fields, electrical forces in fields, and mechanical forces in fields. This is where this is going to come into play. This causes the potential difference, V, voltage, along the wire, which can be used to create current, okay, also resistance, looking at Ohm's law, in the system. Generator does the same thing, but in a coil of wire, not the straight line. So you're just going to wrap it many, many, many times. As the coil rotates, the sides are moving up and down through the field, which results in a current. Specifically, it's alternating current. It's AC, not DC. We were only working with DC current with our breadboards back in topics 5 and 6. Sliding contacts are placed inside the coil to prevent twisting. Okay, those sliding contacts are going to prevent twisting. As the coil rotates, but this causes friction, which eventually wears away at them, and that's also why you're not going to have a perpetual motion machine, right? Because there's going to be some wear and tear on that. It's not going to be 100% efficient. So an alternate is by using magnets. Okay, alternate way of doing this is by using magnets. So like MRIs, for instance, there's a lot of magnets in there, but AC is still created, which is good. You do want that. World energy sources. In order to do work, energy must be able to be degraded, spread out. If already at the same temperature, then no more degradation can occur. Therefore, no more work can be done. So you want a variety of temperatures. You want to be able to manipulate that temperature. It needs to be the variable that you can control. Things that are hot, like the sun, and things that contain ordered energy are used to acquire work in the physics sense. Wow, guys, that's a good one, okay? Make sure you do look at that there. Here's just a nice graph showing you, our pie chart, showing you the world energy uses of coal, natural gas, oil, nuclear power, hydroelectric, biomass, other renewable sources. We are going to chat about every one of those throughout these notes. Fuels are things that are hot. Fuels are substances that can release energy by changing chemical or nuclear structure. So this is kind of like a checkpoint slide. Do you remember this? You should be able to from previous notes in this video. Coal. It's composed of plants. Did you know that? Coal is composed of plants that have died millions of years ago that are converted by layers of sand and mud. They are dug up from the ground here on Earth due to mining or open cast mining, and it is called a fossil fuel for obvious reasons. It is a fossil fuel. It is also labeled as non-renewable. Okay, coal is a non-renewable resource. To release the energy in coal, it must be burned. By burning this coal, you're going to release CO2, carbon dioxide, into the atmosphere. This release of CO2 is a greenhouse gas. We'll talk more specifically about greenhouse gases later, but just to get the ideas flowing here, there's greenhouse gases that are going to be present. Oil now. So you just talked about coal, now we're going to talk about oil. It's like the next layer up if you were like digging a nice core into the earth. Overtaking coal as the most important resource of energy rather similar to each other. Fossil fuel, oil is a fossil fuel that is classified as a non-renewable resource. Once it's gone, you can't get it back. Formed from microscopic organisms that sank to the bottom of the sea, that over time have been turned into rock that was pressed into oil and gas. So you would have coal at the bottom layer, oil in the next layer, gas on the top layer. It is easier to extract than coal. It can be pumped up instead of dug out of the ground. It has to be burned though, so since it has to be burned, oil is going to give off CO2, thus greenhouse gas. Natural gas, colorless and odorless in its natural form. There's an odor that is added to help detect leaks, or like in the chemistry classroom. We put smells into it, scents into that, so you can smell if it is leaking. It is formed at the same time as oil, and it's trapped above the layer of oil. So natural gas is found above oil. Low temperatures, less gas than oil is formed. It is cleaner. It's cleaner burning than oil and coal, but I never said anything about it not being a greenhouse gas. Here's some typical compositions of some natural gases: methane, ethane, propane, butane, carbon dioxide, also oxygen, nitrogen, hydrogen sulfide, and some rare gases such as helium, neon, xenon. Non-renewable resources recap. You have 3 of them here. The first that we discussed was coal, which is at the lowest layer. Then you have oil that is trapped on top of that. And then you have natural gases that would be on top of that. Coal has to be dug out. Oil can be pumped out of the ground. Great diagram here, guys. Take a second and make sure that you do look at this diagram. I wouldn't be too surprised if you have some paper 1 question about where is oil, coal, natural gases. Renewable resources. Renewable resources are cleaner than fossil fuels, but the disadvantage is high startup cost. Living plants convert sunlight plus CO2 into plant matter, which can be used for fuels. This data was taken from Australia, which shows you a lot of good information on how much of the renewable resources they use. We're going to stop here for the first video and pick up in a second.